Hello and welcome everyone to my new video, and again a special episode. And few days ago I posted a poll on Twitter, and I asked if anybody is interested in knowing how to train a sentiment prediction model using BERT, and it got quite a lot of votes on yes. So a total of 391 people voted, and that's amazing. So I decided to make this video, and now there's a lot available on sentiment prediction everywhere on the internet. But I'm training a very basic model, and I'm going to show how to do it in a much better manner. So to start with, I was working on a different sentiment dataset, but yesterday a guy on LinkedIn suggested this dataset, the dataset that he was working on. So I thought, why not build a model on this dataset? So this is the dataset from IMDB. It has 50,000 movie reviews, and they are labeled as positive or negative. So you can see here that there are the reviews and labels are positive and negative. So we are not going to do any kind of exploration, data exploration here, because it's not needed in this case. So we already know that there are 25,000 positive and 25,000. Sorry, this is okay. So this is 25,000 for testing, 25,000 for training the model. But we also know that the dataset here consists of equal number of positive and negative samples. So we can build a model quite quickly and easily. And in this video, I'm not going to compare different models, but I'm just going to create a model for using BERT, and I'm going to show you how easy it is. So what are the things that you need first? First, you need these two folders, source src and one input folder. And inside input folder, I have put BERT base uncased folder. It has the config file, the PyTorch model, and the vocab file. So this is how the vocab file looks like. If I scroll down a little bit more, I will see some words. So you can see this is the vocabulary, and this is the configuration file for BERT base, and there is a PyTorch model.min. So now I have also downloaded the dataset from the same source here, which is review and sentiment, two different columns. It's a CSV file. So we have that, and now we can start building or coding the model itself. So if you want to download the BERT base uncased, you can use the dataset that I've uploaded here called BERT base uncased from this link, or you can just download it from Hugging Face transformers. So to start with, we will first we will go in steps, and it's very important that you do it in the right way. So we will first create a file called config, and my config.py will contain only what I need the most. So okay, I will need some kind of, so it contains the configuration. So I will need some kind of maximum length that I'm looking at. I need train batch size. Let's say it's 8. I need validation batch size. I will keep it to 4. I need epochs, the number of epochs I'm training. Let's say it's 10. Accumulation is 2. What accumulation is, I'll come to that, so hold on. Then I need BERT path, and my BERT path is in my input folder, BERT base uncased. And then I need where I want to save the model, so model path. Let's say I'm saving the model in the same folder as src, model.bin. And training file is input/ imdb.csv, and then I need a tokenizer for BERT. Now, so in this video we are training only one model, so we need only one kind of tokenizer. So I'm putting it here. If you have multiple tokenizers, watch my other videos in which I have tokenizer dispatcher and model dispatcher. That gives you a better way to evaluate different types of models. So let's import transformers, and then I have transformers dot BERT tokenizer, dot from pre-trained, and instead of providing BERT base uncased here, I'm just going to provide the path to the model. So that will be BERT path, and then I have to lower case to true. So this is how my config file looks like. You can see like not much stuff, and these things I need everywhere. I needed them during training and also during prediction time, so it's better to just have them at one place. So now we can move to the next files. So let's start with the model first, and here we have model.py. Let's start with that, calling it model.py, and inside model.py here you will define the model. So what is our model? So I'm going to create model in such a way that you can reuse it, import transformers, and you can also experiment a little bit more. Import torch.nn as nn. So we need these two Python packages, torch and transformers for the BERT model itself. And I'm going to create a class BERT base uncased. So that's our model that comes from nn.module. And then you define an init function, self, and that's it. And then you say, okay, it's a superclass of the same name which is here, and self init. Okay, so now you're done with this part. Now you can load the model itself. So I will say self.BERT will be transformers.BERT model dot from pre-trained, and this takes path of the BERT model. So I can just import here. I can import config, right? So I got the model, and here I can say that my path is config.BERT path, right? Do I need anything else here? So I don't think so. So that gives you the model itself. So let's just keep it in one line if I don't need anything else. And then I define a few more things. So I will say BERT drop. That's my dropout. So I will say, okay, 0.3 dropout. And I want a linear layer or an output layer. So I will say self.out is nn.linear. Now I already know that BERT model, the BERT base that I'm using, has 768 output features. So I'm going to say 768, 1. Now why 1? Because it's a binary classification problem, and we just want a value between 0 and 1. You can also do 2 and convert it to, then you have to use a different loss function, but I'm going to keep it very simple. So def forward, and now if you see this BERT model, it takes multiple kinds of input. So one input is the input IDs, so I'm just going to call it IDs. Another one is attention mask, just going to call it mask, and token type IDs gonna be the same. Once you have that, you get two outputs. So output 1 and output 2 from BERT. So self.BERT, so that's the forward function IDs. Then you have attention mask. Let's do it like this. So you have IDs, then you have attention mask is mask, and token type IDs is my token type IDs. So we got these two outputs. So yeah, so we have these two outputs from BERT. Okay, so like out1 is your sequence of hidden states for each and every token, so for all batches. So like if you say if you have 512 tokens, that's our max len. So you have 512 vectors of size 768, and that's for each batch. And this is only the last one, only the first one, so the CLS token of BERT. So this is called last hidden states, and this one is the pooler output from the BERT pooler layer. And you can do a lot of things here. So you can use out1 and you can perform some kind of average pooling, max pooling kind of things, and you can use this one or you can just use this one. So what I'm going to do is I'm going to remove this and just using O2, and probably just change it to O2. And so you have that, and then this gives you a vector of size 768 for each sample in the batch. So what I'm going to do is I'm going to say, okay, my BERT output is first I apply the dropout self.BERT underscore drop, and this takes O2, and then I pass it to the linear layer. So my output will be self.out, and here will be BO, BERT output, whatever we have got, and return output. So now you see, like this is our model. So everything is from here to here, very simple, and you can make a lot of changes inside here, so in order to improve the model, but I'm not going into too much details there. Take a look at BERT model from Transformers, and it has a very good documentation. You will understand everything very clearly. And now this output is linear, so it's just going to produce a number. So now we have the model, and now we can move to the next step and try to create the training and evaluation functions, so that you need to when you're training the model. So we go to so we create a new file. I'm gonna call it engine.py, and that's going to consist of my training and evaluation functions. So let's say I call the training functions train fn, and this takes my data loader, this takes the model itself, it should also take input optimizer, it should take what kind of device you're using, and it should also take accumulation steps, so the accumulation that we defined earlier. So we have all these arguments, and then we can put the model in training mode, model.train, and then we loop through each batch. So I say, okay, for batch index comma dataset in my let's add tqdm just to monitor the progress from tqdm, import tqdm. tqdm, and then you have enumerate. We enumerate batches. Data loader. Okay, and total is len of data loader. This is the total number of batches that we have. So now we need to extract some stuff. Okay, but to extract some stuff here, so we do some things here, and then we also create a def eval function, and we do some things there. So this is not ready. This is not ready because we have come to defining the training and evaluation functions, but we didn't define a very important thing. That's the data loader itself. Actually, we should do it before everything. So let's define the data loader. It's very simple. So you have a new file called dataset.py, where I'm going to define the data loader. So my data loader is BERT dataset. Okay, I don't need to inherit from anything. Init self, and this should take some inputs like the review text, the target. It should take a tokenizer and maximum length, but we already have that in config, right? So what I'm going to do is I'm going to say import config. Okay, so self.review is review, the review text, so that's a list, and you have self.target, so that's a list of numbers 0 or 1, and we say okay, what is the total length? Self return len of self dot review. So that's the total length of your dataset, and then you need the get item function. So now you have the get item function, and the get item function takes an item and returns your items from the dataset. So like IDs, token type IDs that we will create. So we have self and item, or you can also say item index. So we do review, we just convert it to string, self dot review, just for a sanity check kind of thing, so that we don't have problems when we have some numbers or something. And review will be, so I'm just going to remove all the weird spaces, and then I have to encode it. And for encoding, there's a very nice function in tokenizers. So let's say here my self.tokenizer is config.tokenizer, and self.maxlen is config.maxlen. So now everything is set properly, and I can do self.tokenizer.encode plus. So encode plus can encode 2 strings at a time. We have only 1 in this case. So we are going to say review, comma, none, review, comma, and then the second string, which is none. And then we are going to add special tokens to true. That adds our special tokens called CLS token or SCP token. So you have CLS, then the tokens from the text, then a SCP token. If you have a second string, then after SCP token you have the second string, and then you have SCP token again. So we define max length is myself dot max length, and this is done. So now input will return your inputs. This will return your, this will be your IDs. So IDs will be inputs IDs, sorry, input IDs, I think. If there is an error, we will see that later. And then this one will be your mask, which is your attention mask, and token type IDs. So token type IDs in this case is just going to be one for everything. So we don't even probably need it because mask and token type IDs are the same in this case because we have only one string. And you say what is your padding length. My padding length will be self dot max length minus the length of IDs. Okay, so for BERT you need to pad on the right side, so we start padding. IDs will be IDs plus, we pad with zeros, 0 times the padding length, and you do the same for mask and token type IDs. So once we have all these, we can just return what we want to return. So we will return IDs. So now we can convert it to torch tensor, torch.tensor, and to do that we also need to import torch. Okay, so now we can convert it to torch.tensor. So I say IDs and specify a D type. So in our case, D type will be long, and it's going to be the same for all three. So quite simple. Token type IDs, token type IDs. And we also need to return target. So we will return target torch.tensor self.target and take the item, and torch D type here will be torch.float. So now since we have taken a linear layer with one output, so it's torch.float. If you plan to if you plan to have two outputs instead, then you need torch.long, and it also depends on what kind of loss function you use. So for cross entropy you need to use torch.long. So now we can go back to our engine.py and finish that one. So here in dataset we have IDs, mask, token type IDs, and target, and same thing we have to do in engine. So we have to grab them from dataset and then run through the model. So here we are, and we have IDs, so that will be D IDs, so whatever you're getting from the dataset. Token type IDs is equal to D, or was it ID? IDs, mask, token type IDs, target. Okay, so IDs, token type IDs, mask is D mask, and target is D target. Let's call it targets because there are multiple targets in a batch. Okay, so we got all these, and now we need to send them to the CUDA device that we are using. So I'm just gonna say, okay, IDs is IDs.to device, or CPU device, whatever you want to train it on. D type is torch.long, and then we do the same thing for token type IDs, and mask. Got it? Okay, and targets will be the same. So let's just copy paste this one here, and here we have targets to device dot float this time. So we got everything that we need. Now we can do optimizer dot zero grad and then pass it through the model. So outputs will be model, and then here you have what you have in model, IDs equal to IDs, mask equal to mask, and token type IDs is token type IDs. So just to make sure we are doing it correctly, IDs, mask, and token type IDs, we go to model and see, IDs, mask, token type IDs. Okay, so it's correct. So you got that. And now comes the interesting part with accumulation. So we calculate the loss function, and we need to create a loss function first of all. So def loss function takes outputs and targets and returns, and then dot. Okay, we need to import one more thing from import dot nn as nn dot bce with logits loss, and this will be outputs comma targets. Okay, so we got that, we got the loss function. So we calculate the loss here now, and that will be loss function outputs targets. Right, so we have calculated the loss. So now what you can do is you have to do loss.backward first of all, and then you step the optimizer only after a certain number of accumulation steps, right? So we can do we can say, okay, if my batch index plus 1% my accumulation steps, if this is 0, then I do optimizer dot step, and I also do like scheduler dot step. Okay, and then that's it. So we have optimizer.zero grad. We can leave the accumulation for now for this video, just to keep it simple. So I'm just going to remove accumulation from everywhere, and that's okay. Okay, so loss.backward, optimizer.step, scheduler.step. Okay, that's it. That's all you need for training function. And now for evaluation function, we do model.eval, and evaluation function should take data loader, model itself, and does it need anything else? Device. Okay, so now I can copy paste this whole thing and put it here. Okay, for batch index and data loader, IDs, blah blah blah. I don't need this anymore. Do I need to calculate the loss? So let's say we just monitor the accuracy, so I don't need to calculate the loss here. You can calculate the loss, and it's better to monitor the loss in evaluation function, but let's not do that, just to keep it simple. And so we have the outputs and everything, and we can do one more thing here, because otherwise your GPU can run out of memory. With torch.nograd, and just wrap everything inside this. So I missed it in the last video, but a lot of people pointed it out, and then it was okay. And here I can do fin targets. So my final targets is an empty list, and fin outputs is also an empty list. Okay, so now we have the outputs. So I'm going to say fin targets is dot extend. So I'm just going to extend to the list. So I need to get the targets, then I convert them to CPU, and then I detach, convert it to numpy, and convert it to a list. Okay, so this is, yeah, quite interesting. And then I have fin outputs, and I do the same for outputs. But when I do the same for outputs, I can also do one more thing, which is torch.sigmoid. So because we have the linear layer, so I can just do torch.sigmoid to convert it to a sigmoid function, and for that I would need to import torch. Okay, so I got everything that I need here now. So I can just now I can just return. So for everything blah blah blah, when it's done, then return fin outputs and fin targets. Okay, so now we are done with this, the evaluation function and the training function. So we did the config, we have the model, we have the dataset, BERT dataset, data loader, and we have evaluation and training functions. So now we need to train the model finally. So we create train.py. So now we have everything that we need. So it's only the training part that's left. So let's start with the training part. So I'm going to write a function called run. Let's call it run. So def run, and this will be my training function. So first thing that I need to do is import config. So let's load the data using pandas. So we have import pandas as pd dfx, that's my data frame, pd.read csv. So this is config.training file, right? And I'm just going to do fill na with none if there is a na value. Now if you saw the data first, you see the data set has positive and negative, so we need to convert them to binary variables. So you can also do it using label encoder, but here, since there are only two, it's pretty easy to convert it in pandas. So I'm going to say dfx.sentiment is dfx.sentiment.apply, then lambda. So I'm going to do it using lambda x. You can also do map.map, that's also fine. Lambda x1 if x is positive, else 0. So this is just going to map into positive and negative. And now we can split this dataset into training and validation datasets. df train, df valid equal to So to split them, I'm going to use scikit-learn from sklearn import model selection dot train test split. Yeah, so one thing to be noted, like here I'm not doing import star anywhere. So import config, right? Import config, not import star. From config import star, don't do that. So now when you read this file, you will come here and see, okay, from pd.readcsv config.training file. But if I just do from config import start, you will read pd.readcsv training file, then you don't know where training file came from. So it's better not to do that. Make the code more understandable for others. And train test split, so I have dfx, then I can do test size, was it 0.1, 10% of the samples, and I can also do a random state 42, let's say, and stratify equal to dfx dot sentiment dot values. So what stratify does is, like, when it splits, your training and validation sets are going to have the same ratio of positive to negative samples. So once you have that, you can just do df underscore train equal to df underscore train dot reset index drop equal to true. So it just resets all the indices that you have, because you're going to have we are in this index values. So now it's from 0 to length of df train and 0 to length of df valid. And you do import dataset. So now we can build the data loader object. So you can also do import torch here, and then you have training dataset and validation dataset. So train dataset equal to dataset dot BERT dataset. So we have that here, and that takes review and target, right? And tokenizer and maxlen are already imported there. So review will be df underscore train dot review dot values, and target will be df underscore train dot target dot values. So we created the training set. Now let's create the train data loader, and that's torch dot utils, I think, dot data loader. Yeah, and here you have train dataset, and you specify batch size. So that's my config dot train batch size, and then you have what else do you need in training dataset? Number of workers, let's say. So I'll specify 4. You can also put number of workers in your config file. So we have both these, and I'm going to copy paste it here. I'm going to change a few things. So wherever there is train, it should be valid. So let's see if this works. Valid. Okay. And this will be valid in capital. Valid batch size. Was it valid batch size? Yeah. So valid batch size. You don't need 4 workers. So 1 worker, let's say, for validation. Why do you need 4? And device is torch dot device CUDA. We are going to train it on GPU, obviously, and then you have to take the model. So I'm going to do here from model import BERT base uncased. So that's my model. So BERT based uncased. Does it take any input? No, it doesn't take any input. And then you do model, then you have to have like specify what parameters you want to train. So I'd say param optimizer. So this is like the very default from transformers. Model dot named parameters. I take all the named parameters in param optimizer as a list, and then say I don't want any decay for bias layer norm dot bias and layer norm dot weight. This is pretty much the default. And optimizer parameters will be, now you create a list of parameters. So say okay, list of dictionaries params, and I say p for and comma p in param optimizer. If not, so I don't want to have I don't want to have weight decay for layers which have these names, right? So here I'm going to say if not any nd in n for nd in no decay. Okay, then you specify weight decay, how much you want. So I'll say 0.001. So to understand what's happening here, you can just do this part and then print this. You will understand what's happening. I'm not going into details there, I know. And then you need the same for all other parameters and say remove the not and to 0. Okay, and this is pretty much the default. The next thing that we are going to do here is specify a few more things. So now we are ready to train, almost there, but we have to specify what are the number of training steps. So your number of training steps is equal to your length of the full training data. So I'm just going to convert it to int first. Length of df underscore train divided by the batch size, train batch size. So that's in config dot train batch size multiplied by the number of epochs that you have. So config dot epochs. Okay, right. So now you can define an optimizer. So we are going to use Adam optimizer, Adam W from Hugging Face tokenizers. So let's import it here. So from transformers import Adam W, and let's also import the scheduler that we are going to use. From transformers import get linear schedule with warmup. Okay, simple one. Formers. Okay, so now we can define the optimizer which is Adam W, and takes the optimizer grouped optimizer parameters, and a learning rate. So you can experiment with different learning rates. What I experimented with was 3e minus 5. So I'm going to use the same 3e minus 5. So I always start with 3e minus 5 or 2e minus 5. And then you need the scheduler, which is get linear schedule with warm up, and this takes optimizer, number of warm up steps. So I'm starting with 0, no warm up steps, and number of training steps, which will be num train steps. Okay, so we got optimizer, we got the scheduler, and we have everything now, so we can start training. So since I have 2 GPUs, what I'm going to do is I'm going to say nn.data parallel, so convert the model to a multi-GPU model, and I'll have to import torch.nn as nn here. So I converted it to a multi-GPU model. You don't need to do this if you don't have multiple GPUs. So now we can write our training loop. So best accuracy, I say, is 0. So for epoch in range config.epochs, let's import engine, and here we can do engine.training function that takes the train data loader and takes model and optimizer and device. So we have this. Right, now we do the same for validation function. So we have outputs and targets. That validation function is returning all the outputs and targets. Engine dot eval function, and here you have valid data loader and model and device. So if I go here, I will see data loader, model, and device. Don't have anything else. Back to our training function. So now we can calculate the metrics. We can also calculate inside the evaluation function. I decided to do it here. So accuracy will be metrics dot accuracy score, because it's the distribution is 50-50, so we can calculate accuracy. You can also calculate precision and recall. I'm going to say accuracy score. So this takes outputs. I'm going to convert it to a numpy array first. Output, and that's greater than 0.5. If it's greater than or equal to 0.5, it's positive, else it's negative, let's say. So here I have targets and outputs. So this will be my accuracy score. So print, I can just use a f string, accuracy score equals accuracy. Okay, so now you have the accuracy, and now you want to save the model. So let's say if accuracy is greater than best accuracy, then save the model. So torch.save and save model.state dict and save it in config.modelPath. And then you change your best accuracy to accuracy, and best accuracy will become equal to accuracy. So this is going to save your best model, and this is going to run till the number of epochs you have specified in config file, which for us is 10. And then I need to define a main function, score main score, then run the training. Here I'm also forgetting few more imports. So from scalearn import metrics, and I have also used numpy, so import numpy as np. And I think we are good to go. So let's try to train the model now. So I'm going to open a new terminal and go to source directory python train.py. Okay, so I have some syntax problems. Yeah, okay, so I have some syntax problems here. I did not close the bracket. Same here. And let's try to run it again. I still have syntax problems. Okay, so let's see what else is wrong. Oh yeah, I don't need this here. So that should be fine. So these parameters are adjustable, and you should really take a look at different layers and which layers, how much weight decay you want, how much learning rate you want, and you can improve the model a lot more. Okay, so now we go to train.py, and data frame object has no attribute target. Data frame object has no attribute target df.train.target.values. Oh, obviously it's not target, it's sentiment. Okay, it didn't match because some keywords were incorrect. IDs torch.long, something is incorrect. So let's look at what's incorrect in dataset. Torch.tensor, dtype torch.long looks correct to me. Okay, so okay, it should be small. Big blunder. And we can try it again. Okay, so now it's training. But if one of them found on CPU, it's started training, but it's now throwing another error. So module must have its parameters and buffers on CUDA. That is 0. Okay, so did we miss something in train engine? Did we miss some device? Torch.ids, mask, targets.ids, everything is fine. So one of them is on CPU and not on device. Mask, token type IDs, targets to device. Everything looks fine. Let me take. So everything seems good here. I don't know where the error is. Oh yeah, model.to device. So model was not on GPU. That's big error again. So let's see now. Let's try to run it again. And now it's training. Target must be the same size as input. Okay, yeah, so the problem here is go to engine and targets dot view -1, 1, and that should solve this issue. So outputs have the shape of 8, 1, that's a batch size 1, and targets is only 8. So I'm just changing it. Scheduler is not defined. So scheduler seems to be undefined, and here what do we have? Data model optimizer device and scheduler. We need that. And then we need to change it in the training function, training script, scheduler. Clear all this, then train again. So yeah, some errors, but everything looks okay as of now. And now it's has started to train, and you can see, like, I think, yeah, okay, 35 minutes for one epoch. So we are going to let it train. It's going to take a while, but after 1 or 2 epochs you're going to get good results anyways. So now the more interesting part comes, and that part is you have built the model. So now we have to put it in, you have to serve it to your customers. So let's try to create a simple Flask API, REST API, and see if we can put it to not to production, but close to that. Let's see if we can do that. To serve the model, we will use something very simple for now, and we create a new file called app.py, and then we serve it using Flask service. So let's import what we need. So we need import config. So you can also serve using batches, but what I'm going to show you is how you can just simply get predictions for one single sentence. So import, you need dataset. Import, do you need dataset? You don't need dataset. Import torch. And from Flask, import Flask, and from model import BERT base uncased. So you have all that. You initialize the Flask app, and then you define some global variables. So model is none and device is CUDA, and then we create a simple endpoint call. So how you create endpoint using Flask app.route / predict, that's your endpoint, and def predict function, and this should return something. So let's say my response is a dictionary. So response is let's say response let's say response. Inside that we have response again, and that's a dictionary again, and return flask.jsonify response. Okay, So this is your predict function. Now we have to do a lot of things there, but let's hold on. And now this should take the sentence from the end user and try to predict. Right. So what we do is we create def sentence prediction, another function, and that takes a sentence. And now you define tokenizer that comes from your config.tokenizer, and max length is again config.maxLength. So your review is str sentence, and now see everything that you have done in dataset, you need all that. So we will just take all these things. Let's take all of them from here and put them in here. Okay, so inputs and code plus, so everything comes from the training part itself, so we don't make any changes. So the only changes that we do here is IDs is torch.IDs, and here you have mask, and here you have token type IDs, which is this tensor. Now you don't have the targets anymore, so we're going to remove that one. Okay, and now the next part is also something you have already done. So that comes from your models.py. Sorry, it comes from engine.py. So this part here. So I'm just gonna copy all of this datasets, sorry, app.py, and put it here. So I send the IDs to device, tokens to device. I don't need this one, and I have outputs. So now since I have outputs, what I can do is my outputs is torch.sigmoid, and this will be outputs. But there's one more thing that we are missing. So our data loader always returns batches, so we need to add unsqueeze 0. So it just adds one more dimension. So your batch size is 1 now, and everything else should be okay. And here you can return outputs. Now outputs will be it's 2-dimensional, but there is only one value, so we are going to do output 0 0 and just pray that it works. Okay, so we got almost everything now, and then we need to take the input from the end user. So to get data from end user from Flask, you also need to import one more thing, request. And here we write my sentence will be, I can do Flask dot request dot get JSON, and then I can just do request dot args dot get, not JSON, request dot args, sentence, let's say, let's try to see if this works first. Okay, so if name app.run. We have already defined the app. Okay, so let's see if this one first, if this one works. So we start a terminal, cdsrc python app.py. So it's running on this one. So can just copy paste this. Oh no, never use Control C. Control Shift C and go here. Do I have anything? I don't have anything because it was /predict, right? So it has an internal server error, but it seems to be working fine. So it gives me that Flask is not defined. So just gonna say import Flask here, then try to run it again, and let's refresh. Okay, now you get the response, right? So it looks pretty cool. Now all you need is sentence and the predictions. So let's work on that. So you have the sentence predictions. Let me make it a little bit smaller. Okay, this is better. And I didn't see if it printed anything, so let's run it again. Python app.py. So when I refresh this, it returns none because there is none, no sentence. So I do sentence after question mark. I love this video, and the sentence is printed here. I love this video. So you got the sentence that you need. So now what you need to do is prediction will be sentence prediction sentence, right? And that gives you the prediction. So that always gives you the positive prediction. So positive, so I can just say positive prediction and negative prediction because we trained it only on one class. Sorry, not one class, but like we had only one output, and this will be 1 minus positive prediction. And inside response, now you can say positive is my positive prediction, negative is my negative prediction, and sentence is my sentence. So you can also return a lot more stuff here, but we don't need all that. Okay, now it's time to integrate our model. So we can write model is my BERT base uncased, don't need anything here, and then you need to load the state dict in the model. So we're going to try without that first. Device and put the model in eval. Okay, so the model is there now. Model has trained successfully. I trained only for one epoch, by the way. So we have everything, and we're just going to see if it returns anything or if it gives me an error first of all. So internal server error. Okay, self is not defined, obviously, because we forgot a lot of things. So we don't have self anywhere else anymore. It's not a class anymore. Okay, so let's see, let's run it again. Again a server error. Max len is not okay. Max len, it should be max len. Making a lot of mistakes today. And let's see, device is not defined. Should be device in capital. Let's try again. You can also do debug equal to true in app.run, then when you make any changes it's going to reload on its own, so you don't have to reload every time. I should have done that. Yeah, okay, more copy paste problems. Run it again. Oh my god, it's not working today for me, it seems. So I'm going to say model as another argument, and sentence comma model is model. And I really hope this works this time. No, object of the type tensor is not okay. Yes, chart.sigmites.cpu .detach .numpy. Object of the type float 30. Okay, I'm just going to convert this to string. String. Without investing too much time to see how to fix that, because this should work. So we got negative, positive, and my sentence was, I love this video. You see positive score is pretty less, and yeah, that's obvious because we did train the model, but we did not load the model dictionaries, so model weights. So we have to do that. Can do here model dot load state dict torch dot load config dot model path. But there is one more thing that we trained using 2 GPUs, so this will also throw an error. So just to avoid that, I'm going to convert it to data parallel model, and this should work hopefully, but not. I've made a lot of mistakes today, so let's see. So that's my app.py, and I can do okay. Import torch.nn as nn. Now we run it again. So I think it's loading the weights now. That's why it's taking a little bit of time. Okay, now the server is up. So my positive was 42, and now it's 99. So this seems to be working. This video was so bad, and now it's giving me a negative sentiment. You are amazing, great. Let's try this one, and then it's giving me a positive sentiment. And you see it's quite fast, and so we have been able to fine-tune a BERT model on IMDB dataset, and you we saw the result before and after the fine tuning. So you see, fine tuning is always quite helpful. And one more thing I would like to mention, that the accuracy for this model came out to be 93%. So there's a lot of scope to improve. You have to see, like, play around with some learning rate, warm-up steps, play around with what kind of parameters you want to have in the optimizer, what kind of learning rate you want for different layers of the model, and you will be able to improve it further. So that's my video for today, and if you like it, click on the like button and subscribe and share it with your friends. If you have any comments on how I can improve further, let me know. And the code for this will be available in my GitHub repository. You will find the link in the description box. And thank you very much, and see you next time. Bye.